Hello students, welcome to the online video lectures of Physics O-Levels 5054. Today we're covering the first topic, which is physical quantities, units and measurements. I am Faraz Khan, and let's proceed with the recording. So the learning outcomes for this chapter is all of these points that we are going to cover for this. The first is scalars and vectors. We're going to look at what the definition of these two terms is. We're going to determine the resultant of two vectors by graphical methods, which would be in straight line and when they're not in straight line with more than one forces acting on a body. We're going to list the vectors and scalars, different quantities. We're going to look at different measurement techniques and different apparatuses and instruments that we use. And then we're going to look at SI units and their symbols and other instruments for measuring time. All right, so let's begin with this. First is scalar and vector. So scalar quantities are those quantities that have magnitude only. Now, when we're looking at different quantities, when we observe around, we've got a lot of different physical quantities. But the difference in these quantities that makes this classification between scalar and vector is that scalar quantities have magnitude only. Now, a lot of different quantities, let's say, for example, distance. Distance is a scalar quantity since it has got no direction to it. But if you apply a direction to it and make it displacement, now displacement is the same quantity but only in a specific direction. So that becomes a vector quantity. This is the major difference between a scalar and a vector quantity, that a scalar quantity only has magnitude, while when we're considering a vector quantity, it is very important that it has to have a direction as well. So the different quantities are listed here, such as mass, time, distance, speed, volume, density, work, energy, and power. All of these are scalar quantities since they have no direction to them. But displacement, velocity, acceleration, and force are all of these physical quantities that have a magnitude and a direction to them. So direction is very important for these four quantities, which is the reason why they're considered as vector quantities. Now, moving on. Let's assume that we have a mass of 2 kgs. Now, this is the only information that is being given to you. So there's a body that has a mass of 2 kg. Now, they're not saying that a weight is acting in a certain direction or there's any other 2 kg force being applied somewhere. They're just basically saying that it is a mass of 2 kg. There is no information of direction whatsoever given to this phrase, which is why a mass of 2 kg is just regarded as a scalar quantity. If there was a direction attached to it, which would have said that this is a weight acting towards the core of the earth or something like that, we could have said, okay, this is a vector quantity since this has a direction attached to it. But since this is only saying a mass of 2 kg and it has got no information regarding to the direction, we're going to say this is a scalar quantity. Now, moving on. Car with a velocity of 20 meters per second. Now, this, if you look at this, this is saying that there's a body which has a velocity of 20 meters per second. This is magnitude. And then they're adding the information about the direction by saying in the direction of 45-degree northeast. Now they have specified a certain direction to it. They've got magnitude, they've got direction. So magnitude and direction both is what? Vector quantity. Now, a pointed arrow is used to represent a vector quantity and magnitude being the length of the arrow. Now, when you're making vector diagrams, you have to make sure that you predetermine a scale for it. So you've got to choose an appropriate scale, which could be 1 Newton for 1 centimeter or 2 Newton for 1 centimeter, whatever fits the board at regardless, taking into consideration what the question is, you can determine an appropriate scale for it, and then use that scale to draw the length of the arrow. That length of the arrow is what the magnitude of the arrow is. So if they say that the magnitude is, let's say, uh, 20 newtons, and your scale is 2 Newton per centimeter, so the length of your arrow on paper would be 10 centimeters. And then you can use a protractor to measure the angle of the direction, such as in this case, if it is 45-degree northeast, let's say where to we are supposed to draw this vector quantity of car with a velocity of 20 meter in the direction of 45-degree northeast. This is what we're going to draw now. Let's draw this here, all right? So this is, let's say, our car, for example, and this all right. So now this is our x-axis, or you could say this is, or you could say this is the line for the east. All right, so the east is in the right direction, the west is towards the left, the north to the top, and the south to the bottom. All right, so now let's say we have to first find an appropriate scale for it. If it's 20 meters per second, we're assuming, all right, 2 meter per second is 1 centimeter. So if 2 meter per second is 1 centimeter, so if 2 meter per second is 1 centimeter, 20 meter per second would be 10 centimeters. So on paper, your line should be of 10 centimeter. Now moving on, we need to first determine what the 45-degree angle is. You're going to put a protractor at this point where the green dot is, and you're going to measure 45-degree out of it, and then you're just going to simply take an arrowhead line and draw a 10 centimeter line that will represent a 20, this line should be of 10 centimeter on paper, which will represent 20 meter per second, and this angle here should be 45 degrees. This angle here should be 45 degrees on paper by a protractor. This is what you're going to be looking at. This angle should be 45 degrees on paper, and this line should be of 10 centimeter, denoting a 20 meter per second vector. All right. Moving on. The addition of quantities. Now, with scalar quantities, it is very simple and straightforward. Since there is no direction attached to any of these quantities, you're simply just basically adding all the quantities together. So let's say 100 gram of mass is being attached to a 200 gram mass. Since there is no direction attached, you're just simply adding 100 grams plus 200 grams, that is 300 grams in total. Now, for vector quantities, however, there are a few other approaches that we need to take into account. Now, the addition of vector along the straight line to form a resultant vector. So let's assume we've got two different vectors acting on a body but in a straight line. So here let's take another. All right, so this is our body, and let's say we have a one we've got one force here and one force there. All right, now let's say the green arrow is a 5 Newton force and the red arrow is a 3 Newton force. All right, so the green arrow is 5 newtons and the red is 3 newtons. All right, now if we're supposed to find out a resultant vector on this, we're just simply going to add these two forces since they are in the same direction. So we're just simply taking the 3, adding it to the 5. So on paper, when you're drawing this, if the red arrow is a 3 centimeter line and the 5 Newton is a 5 centimeter line, when you draw a resultant, the resultant would be an 8 centimeter line because you're just simply adding these two quantities together since they are in the same direction. So the resultant would be 8 Newton to the right. But let's say that this 3 Newton force was acting on the left. Now what the resultant would be? You've got 5 newtons to the right and you've got 3 newtons to the left. They're in the opposing directions. So the resultant would be 5 Newton minus 3 Newton, and then your resultant will simply be a 2 Newton force acting towards the right. Now this is what the addition of quantities in a straight line is. If they're in the same direction, you're just simply adding them. If they're in the opposing direction, you're going to find out the difference and the resultant would be in the direction of the greater force. Now, let's assume that these forces that are acting on a body are not in a straight line. So for that, we have the addition by the law of parallelogram. Now you have to consider that there are two different forces acting on an object, and now both of these are at an angle. Now first you have to choose an appropriate scale for the two forces, and that is going to be the first step across the board for any vector diagram. You have to first choose an appropriate scale for it. Then you're going to complete the parallelogram. Now a parallelogram has a set of parallel lines. So the two set of parallel lines, and that what we're going to do is just we're going to complete that parallelogram, and what the diagonal is going to be will be the resultant of the forces that are acting on it. So let's complete this diagram. We're just going to simply take this and exactly just map it right here. We're going to take this, and what we're doing is we're just completing this parallelogram here. So That's how you complete a parallelogram. All right. So the arrow of one to the bottom of another, the arrow of one vector to the bottom of another, and where the two heads meet, that's your endpoint, is taking this line, completing the diagonal. And so this dotted line, which is also going to be an arrow line, let me make this an arrow line so it's easier to understand. This arrow line is the diagonal and the resultant of the addition of these two vectors. Now, one thing that you've got to note is that it's not being done here, but every resultant force is supposed to be denoted by a double arrow line. So when you make this on paper, you're supposed to make a double arrow line, and that's how you do the addition by the law of parallelogram, where the diagonal is the resultant of the addition of the forces at different angles. Now, moving on. The SI base quantities and units. Now, there are different base physical quantities, and they've got different names for it. And the symbols are very important because we're going to use them just the way they are. So for length, the name of the base unit is meter and the symbol is a small m. Now make sure you take great care of the lowercase and uppercase letters in all symbols, since they're going to remain the same. If it's a lowercase letter, it is going to remain a lowercase letter throughout the entirety of its course. So you cannot write a smaller, a capital M in place of a small m. It will not be considered as an SI unit symbol. So for length, the name of the base unit is meter and the symbol is small m. For mass, it's kilogram and the symbol is kg. For time, it's second and the symbol is a small s. For electric current, it's amperes. For thermodynamics, it's Kelvin. For luminous intensity, it's candela. For amount of substance, it's moles. So moving on to the SI prefixes. Now, as the numbers grow, it is very important that we use these SI prefixes to make it easier for us to understand. So now, let's say if you've got 10,000 grams, you can just simply write it as 10 kgs. All right. So what these prefixes denote is these powers attached to them. So 10 to the power 6 is mega and the symbol is m. 10 to the power 3 is kilo and the symbol is k. 10 to the power minus 1 is deci and the symbol is d. 10 to the power minus 2 is centi and the symbol is c. 10 to the power minus 3 is milli and the symbol is small m. 10 to the power 6 is micro and inverted. A flipped U is the symbol for micro. Now, moving on, for the different, these are the different instruments that we're using to measure length. Now, the SI unit for length is meter, a small m. When you'll be using the meter rule, the eye must be placed vertically above the mark to avoid any parallel error. Now, To understand what a parallax error is, let me just quickly tell you what this is. When we're taking the measurements for any body, and let's say we've got a scale at the bottom of this. Let's say we've got a scale at the bottom of this object. Your eye must be placed vertically above. This is where your eye must be placed. This is where your eye should be. This is where your eye should be. Now let's say that your eye is not vertically above the mark. So what you're doing is basically, let's say if you're looking at an angle, and this is where you're looking from at, all right? Now this is a problem because you can see the difference between where your eye is being pointed at and where the object ends. This difference in between is what we call a parallax error, and this is what we need to avoid. So we need to make sure that our eye is placed vertically above the object to avoid any parallax error. Now, looking at the different instruments that we can use, these are according to the length in question. So if it's and if we're supposed to measure a length of several meters, we're going to use a measuring tape, and the accuracy of that instrument is about 0.1 centimeter. If it's several centimeters, we can use a meter or a half meter rule, depending on how much is it, and the accuracy would also be 0.1 centimeter for a meter or a half meter rule. Then moving on to, let's say the length is between 1 centimeter and 10 centimeters. You can use a Vernier caliper for it, and the accuracy of that instrument would be 0.01 centimeter. But if it's less than 2 centimeters, a micrometer screw gauge is the appropriate instrument, and the accuracy of it is 0.01 millimeter. Moving on to our first main instrument, that is the Vernier caliper. Now it is used for more accurate measurements, and the accuracy is plus minus 0.01 centimeters. Now it has both inside and outside jaws for internal and external diameters. You can see these jaws on top of the Vernier caliper. These are inside jaws for internal diameters, and these are the outside jaws for external diameters. Now, how are you going to take the reading on a Vernier caliper? Now, this one that is going in between, this here is the main scale, and this is the vernier scale. Now, let's look at these steps on how to take the reading, all right? So the first part is you've got this main scale here, so it's 3.1, 3.2, 3.3, and you can see the vernier scale starts, the 0 is between 3.3 and 3.4. So the first two readings from the main scale is that it's somewhere between 3.3 and 3.4. So the reading is 3.3, and the second decimal place we're going to find out from the vernier scale. All right, so we're going to see where these two lines on the main and the vernier scale match. So these lines don't match, these lines don't match, these don't match, these don't match. It matches at the fourth marking. So 0.04 centimeters, we're just going to add in 3.3, and your final reading would be 3.34. So what we're going to do, so let's get over with this. We're going to look at the main scale first. We're going to see where the 0 from the vernier scale starts. All right, so the line before that is your answer. So if it's between 3.3 and 3.4, you're going to take 3.3. Then you're going to look out where the main scale and the vernier scale intercept, and the markings appear as straight line from the vernier to the main scale. So where these lines are in a straight line, that's where your marking for the vernier scale is, and then you just add it to the main scale reading, and that's your final reading. So in this case, it's going to be 3.3 from the main scale, 0.04 from the vernier scale. Your final reading is 3.34 centimeters. Moving on to micrometer screw watch. It is used for very accurate measurements of a diameter of an object and can only be used for lengths up to 25 millimeters. The accuracy of this is plus minus 0.01 millimeters. Now, this fixed bar here is the anvil. This is a spindle which is controlled by this thimble and the ratchet. This is the main scale here, and this is the thimble scale. This line going by is the datum line. Now, when we put an object in this, we turn the thimble scale and we tighten it up by the ratchet, and then what we look at is we look at these numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 8.5, and then we don't see the 9. So 8.5 is what we've got, and then a few other millimeters that we're going to achieve by the thimble reading. So 8.5 is what the sleeve reading is. The one on top are these are going by the period of 1. So 5, 6, 7, 8, and these ones niche, these below are these 0.5. So 5, 5.5, 6, 6.5, 7, 7.5, 8, 8.5, and then a few millimeters. Now the few millimeters are, we're going to look at the thimble scale and where this line matches the datum line. So a thimble scale has 50 divisions, which means uh, every division is about 0.01 millimeters. So this datum line here matches 40 millimeters, 40 divisions on the thimble scale. So it translates to 0.40 mm, which we're just going to add in our sleeve reading, which was 8.5. So 8.5 plus 0.40 mm, the final reading would be 8.90. Now there are different kinds of errors. If when you close this spindle and there is no object, your datum line and your thimble scale should look like this. But if there is a positive error or there's a negative 0 error, let's say there's a positive 0 error, like you can see that there's a positive 0 error of 0.02 mm. So what we're going to do is we're going to deduct 0.02 mm from this final reading. But if there's a negative 0 error, that means the 0 from the thimble scale is above the datum line. We're just going to add the error into the final reading. So like here, you can see it's 0.04 mm is the error. So we're just going to simply add this into the final reading. So a negative 0 error is added to the final reading, a positive 0 error is deducted from the final reading. Now, moving on to the measurement of time, the SI unit for time is seconds. Now, as we know that all of these watches or clocks are based on some event or some repetitive motion, vibration, which is called an oscillation. So the time taken to make one complete oscillation is called a period of an oscillation. Let's say you've got a pendulum. So as you know that a pendulum swings, so from one end to the other end back is one complete oscillation. So every clock or every instrument that measures time is based on some sort of repetitive motion, and that oscillation is what we consider as a period of an oscillation. Now, moving on to the measurement of time with the different types of clocks, their uses and the accuracy. So atomic clock measures very short intervals of about 10 to the power minus 10 seconds. A digital stopwatch measures small short time intervals in minutes and seconds to an accuracy of plus minus 0.01 second. An analog stopwatch measures short time intervals to an accuracy of plus minus zero point 0.1 seconds. A ticker tape timer measures short time intervals of 0.02 seconds. A watch measures long time intervals in hours, minutes, and seconds. A pendulum clock is also the same. A radioactive decay clock measures in years the age of the remains from thousands of years ago. Now, moving on to the different types. So, a pendulum clock uses the elastic potential energy in the coil springs of the gravitational potential energy of a hanging mass to keep the pendulum running. So, a mass is attached uh, to a string, and it's like a pendulum, so it swings from one end to the other and back. So this complete motion is what measures the time. So it could either be uh, using elastic potential energy in the coil spring, which could be powered by the battery, or it could be from a hanging mass, and it could be powered by the gravitational potential energy. Uh, when we're looking at watches, it uses quartz crystals, vibration, and a small battery to measure long intervals of time. For stopwatches, it is used for very short intervals of time, and it involves a human reaction error. So now looking at a human reaction error, what this is when you look at the event at which you're supposed to start the stopwatch, and then you, from looking at that event happening and the delay till your hand pressing that button on the watch, that delay in time is called the human reaction error. So this manual operation uh, creates the error, which is about zero point 0.3 to 0.4 seconds. So it really depends on the agility and the concentration of the person, but it is from 0.3 to 0.4 seconds almost. Now moving on to a ticker tape timer. A ticker tape timer is an electrically operated device which marks very short intervals of time onto a tape in the form of dots. So a timer is connected to an alternating electricity supply, which causes the metal strip attached to the timer to vibrate at about 50 times per second. So by means of a carbon paper disc, the vibrating metal strip in this causes the paper tape that is pulled past the timer to record about 50 dots in 1 second. Uh, so the time interval between two consecutive dots is about 0.02 seconds. And so it's the kind of device that measures time in 0.02 intervals or ticks, which gives it the name ticker tape timer. Now, moving on to our practice examples. Now, we're supposed to look at these two vector quantities and decide what the resultant of this is. Now, as you can see, one of this vector is in the right direction and the other is in the top right, so east and northeast direction. The resultant would also be towards the right, moving to the top. What we're going to simply do is we're going to complete the parallelogram, and by that we'll get the answer, which is B. Moving on to the next, we have to tell if mass is scalar and if acceleration is scalar or vector. So as we've studied in the first few slides of this tutorial, that mass is a scalar quantity and acceleration is a vector quantity. So B is the correct answer for this. The next question is, the diameter and length of a thin wire, approximately 50 centimeters in length, are measured as precisely as possible. So a thin wire which is approximately 50 centimeters in length. For length, we're going to have to use a rule, a half meter rule or a meter rule. And then it's a thin wire, so a micrometer screw gauge is the most accurate instrument for this reading. So the answer is A. Moving on to the next, we have to find out the reading here. So 5, 6, 7, 7.5, and then the datum line touches at 0.14. So 0.11, 0.12, 13, and 14 is where the datum line touches. So 7.5 plus 0.14, 7.64 is the answer to this question. Now, forces of 25 Newton and 40 Newton act on an object in the direction shown. We're simply going to do is we're going to take this arrow, map it here, take this arrow, map it here, and then we're going to draw a diagonal which is going to be in the direction the same as B. So B is the answer for this. Let me just draw this so it's clear as to how we can draw this. We'll take so 25 Newton right here, and then a 40 Newton line. So our diagonal right here. So it's pretty close to B. So B will be the answer for this question. A length of copper pipe of uniform cross section and several meters long carries water to a tap. Measurements are taken to determine accurately the volume of copper in the pipe. Which instruments are used? So we'll need the length of the pipe, and we're going to need the internal diameter of it. So for the internal diameter, we're going to need calipers, and if it's a several meter long pipe, we're going to use a tape for it. So D is the correct answer for this. Remember, we cannot use a micrometer screw gauge for this because a 2 centimeter length cannot be measured by a micrometer screw gauge. Now moving on to the next question, we have to find the zero error in this. So 0 from the main scale, 0, 0.1, and then the Vernier scale starts. So the first reading is 0.1. Now we're going to look where these lines match from the main and the Vernier scale. So they match at 0.04 at the fourth marking. So 0.1 plus 0.04, 0.14 centimeter is the zero error on this Vernier caliper. Moving on to the next question. Which of the following groups of physical quantities consist only of scalar? as we studied in the first slide, acceleration, velocity are both vector quantities. So mass, speed, and time, option D is the correct answer. Moving on to the next question. One oscillation of a swinging pendulum occurs when the bob moves from X to Y and back to X again. Using a stopwatch, what would be the most accurate way to measure the time for one oscillation of the pendulum? Now, as we have realized that there is a certain human error attached to looking at the event happening and then pressing the button on the stopwatch, we're going to try to minimize that human error by distributing it across a number of oscillations and then dividing it by the same number of oscillations. So what we're going to do is we're going to time 20 oscillations and then we're going to divide them by 20 to find out the time for one oscillation. What this does is that your human reaction error that is achieved at the start or at the end of the swinging motion, that is being distributed across 20 oscillations. So we're minimizing that error. So B is the correct way of timing any pendulum. That is, you time 20 oscillations and then you divide it by 20. Thank you so much. If you've got any questions, put them in the comment box below and I will reply to them. Happy learning. Thank you so much.